Hello students, this session is on transformers. Myself, Bharat Vaike, Assistant Professor, Department of Electrical and Electronics, Malnad College of Engineering. So one of the advantages of using AC in our electrical power system is that the AC voltage can be either increased or decreased as per our requirement. So to reduce the copper losses, also known as the I square R losses, which occurs during the transmission of electric power. So we use high voltages in AC transmission system. If the voltage is increased to a higher level, proportionately the current will decrease and hence the I square R losses will also reduce. So transformer is an essential device in AC system for stepping up or stepping down the voltage. Normally, the transformer terminals are not marked as primary and secondary, but they are marked as LV side and HV side, low voltage side and high voltage side. So primary and secondary depends on the connections basically. So here the same transformer can be used as a step up transformer or as a step down transformer. So when the transformer is used as a step up transformer, the LV side is connected as primary and the HV side is connected as secondary. So then the primary voltage will be less than the secondary voltage and the number of turns in the primary winding will be less compared to the number of turns in the secondary winding. Similarly, when the same transformer is used as a step down transformer, the HV side is connected as primary and the LV side is connected as secondary. Here, the primary voltage will be greater than the secondary voltage. Also, the number of turns in the primary winding will be greater than the number of turns in the secondary winding. Next, transformer is a static device. It doesn't consist of any moving parts, but during practical operation, it vibrates a little bit, because of which you may hear a humming sound. So this is because of magnetostriction. But otherwise, generally speaking, transformer is a static device. Hence, there will not be any losses occurring due to friction. So because of this, the efficiency of the transformer will be very high, normally greater than 95%. Last point, transformer is always rated in kVA, kilovolt ampere. So this is because the operating power factor of the load will always be unknown. So that is why transformer is always rated in kVA. So next is classification of transformers. So transformers are broadly classified into two categories based on the construction. The first one is core type transformers. The second one is shell type transformers. So in core type transformers, as you can see in figure 2, so the LV and HV windings, in other words, the primary and secondary windings are situated side by side on each limb. Okay, so these type of transformers are normally used in electrical power systems. So in power and distribution transformers, power transformers are the one which are used in transmission systems, and distribution transformers are the one which are used in distribution systems. So when we come for shell type transformers, as you can see here, both the primary and secondary windings are situated on the same central limb, and these type of transformers are normally used in low power applications like in electronic circuits, power electronic converters, etc. With respect to the construction of core type and shell type transformers, so in both of these, the transformer core is made up of thin silicon steel laminations. So laminations are thin sheets of thickness of around 0.5 mm, and each of these laminations are separated from one another by a layer of varnish. Okay. So this is done to reduce hysteresis loss and eddy current loss. Finally, the laminations are stacked together and are riveted for mechanical stability. So when we go for the construction of core type transformers, for small transformers, the core can be of rectangular or square cross section. But for large transformers, the core is of cruciform or circular cross section normally. As discussed before, the HV and LV windings, in other words, the primary and secondary windings, are situated side by side on each limb of the core. And the windings are made up of copper coils, which are insulated using enamel, which is transparent, and the winding is cylindrically wound like this. When we go for the construction of shell type transformers, as you can see here, the HV and LV windings, the primary and secondary, are situated on the same central limb. Here also the windings are made up of enamel insulated cylindrically wound copper coils. But here, as you can see, the windings occupy only a smaller portion of the core. With respect to the basic principle of operation of a transformer works on the principle of Faraday's laws of electromagnetic induction and mutual inductance between two coils. The primary winding of the transformer can be an LV winding or a HV winding and has N1 number of turns and is connected to the AC supply. Similarly, the secondary winding has N2 number of turns and is connected to the load. When an alternating voltage V1 is connected to the primary winding of the transformer, an alternating current I1 starts to flow through the primary winding. So this alternating current will set up a flux phi in the transformer core. This phi links with both the primary winding as well as secondary winding. When flux links with the primary winding, a self-induced EMF E1 is induced in it, whose equation is given by E1 is equal to minus N1 d phi by dt. Here N1 d phi by dt is given by the Faraday's laws of electromagnetic induction, and this minus sign indicates that the self-induced EMF E1, whose direction is opposite to that of the supply voltage V1. So V1 is equal to minus E1. Similarly, when flux phi links with the secondary winding, a mutually induced EMF E2 is induced in it, whose equation is given by E2 is equal to minus N2 d phi by dt. Here flux phi is the common factor which is responsible for the inducement of EMF in the primary winding and the secondary winding. Hence, these two equations can be equated. Therefore, we will get an equation in the form like E2 by E1 is equal to N2 by N1, which is this ratio is referred as transformation ratio and is denoted by K. When the secondary of the transformer is open circuited, V becomes equal to E. Therefore, V2 by V1 is equal to N2 by N1 and is denoted using K. So now, assuming that the transformer has no losses and the efficiency of the transformer is 100%, the power on the primary side of the transformer can be equated to the power on the secondary side of the transformer. So V1 I1 cos phi can be equated to V2 I2 cos phi. So in this equation, cos phi and cos phi will get cancelled and we will get the equation in the form I1 by I2 is equal to V2 by V1. Now referring to the previous slide, V2 by V1 is equal to N2 by N1. I can say that I1 by I2 will be equal to N2 by N1, which is nothing but the transformation ratio and is denoted by K. Now we have to derive the EMF equation of a transformer. So let us consider that an alternating voltage V1 with the frequency F is supplied to the primary winding of the transformer. So because of this, an alternating current I1 starts to flow through the primary winding. So this alternating current I1 will induce flux phi in the transformer core, whose equation is given by phi is equal to phi m sin omega t. So this equation is in the form E is equal to Em sin omega t. So this flux phi links with the primary winding, and a self-induced EMF E1 is induced in it, whose instantaneous value is given by E1 is equal to minus N1 d phi by dt. So let us substitute phi m sin omega t in the place of phi. We will get this particular equation. Now let us differentiate phi m sin omega t with respect to time. We will get omega n1 phi m cos omega t. So here this omega is equal to 2 pi f. Therefore we will get this equation. If we want to write cos omega t in terms of sine, we have to write it like sine omega t minus 90 degree. So this particular equation is with respect to the instantaneous EMF, instantaneous value of the induced EMF E1. If you want to get the equation for the maximum value of the induced EMF, which occurs at 90 degree, so we have to substitute sine 90 here. So sine 90 will be equal to 1. So therefore EM1, which is the maximum value of the induced EMF of the primary winding, is equal to 2 pi f n1 phi m. If you want to write the same equation in terms of RMS value, you have to divide it by root 2. So 2 pi f n1 phi m divided by root 2 will get E1 is equal to 4.44 f phi m n1. Similarly, we can write the equation for the induced EMF in the secondary winding also, which is given by E2 is equal to 4.44 f phi m n2. Here f is the frequency, phi m is the maximum flux in the transformer core, and n2 is the number of turns in the secondary winding. Finally, note that in an ideal transformer, E1 is equal to V1 and E2 will be equal to V2. Now let us discuss about the power losses occurring in a transformer. Transformer is a static device, means it doesn't consist of any moving parts, hence there will not be any friction and windage losses. Friction losses are the one which occurs because of the moving parts in a machine, whereas the windage losses are the one which occurs because of the opposition offered by the wind. So the losses occurring in transformer are purely static losses. So these losses can be referred in two categories: constant losses and variable losses. Constant losses are core and iron losses, and variable losses are copper losses. Further, constant losses can be subdivided into two categories: hysteresis loss and eddy current loss. So first let us discuss the core loss, which comprises of hysteresis loss and eddy current loss. So hysteresis loss occurs because of rapid magnetization and demagnetization of the core because of the sinusoidally varying alternating flux. So if we consider one cycle of alternating flux, so first the core will get magnetized and it will get demagnetized. Again, the core will get magnetized in the reverse direction and it will get demagnetized. So in one complete cycle of the flux, so the core will get magnetized and demagnetized for 2 times. If we consider a frequency of 50 Hertz, the core will get magnetized and demagnetized for a total of 100 times. So this magnetization and demagnetization will cause the core to expand and contract. So this expansion and contraction will generate heat, and the power is dissipated in the form of heat. So the equation for hysteresis loss is given by WH is equal to P into B max to the power 1.6 into F watts. Here P is a constant, Bmax is the maximum flux density in the core, and F is the frequency. So to reduce hysteresis loss, the core has to be made up of high permeability material. So if high permeability material is used, then the expansion and the contraction will be less. Hence, the heat dissipation will be less. So that is why the core, normally the core is made up of high permeability silicon steel material. Next is eddy current loss. Here, the transformer core is also made up of conducting material. When the alternating flux links with the core itself, it induces EMF in the transformer core. This EMF will set up a circulating current in the transformer core, because of which the power is dissipated in the form of I square R losses. The eddy current losses are represented by using this equation, where WE is equal to Q into B max square into F square. Here Q is a constant, Bmax is the maximum flux density in the transformer core, and F is the frequency. Eddy current losses are normally reduced by making the core of thin silicon steel laminations, each of which are insulated from one another by a layer of varnish, hence creating a high resistance path for the eddy currents. As the cross-sectional area of the laminations are very less, the eddy currents are reduced. Hence, the power losses are also reduced. The total core losses are combination of hysteresis and eddy current losses, which depends on the maximum flux density and frequency. So maximum flux density depends on the supply voltage, which is constant, and frequency is also constant. Therefore, the core losses are practically constant. Next one is copper losses. Copper losses are also called as I square losses. So these losses occur because of the ohmic resistance of the primary and secondary windings, which is given by I1 square R1 plus I2 square R2. If the resistance of secondary winding is referred with respect to the primary side, so the equation becomes I1 square R01. If the resistance of the primary winding is referred to the secondary, so the equation becomes I2 square R0. So copper losses are normally proportional to the square of the current or the square of the kVA rating of the transformer. So now coming to the efficiency of a transformer. The efficiency of any electrical machine can be represented as the ratio between the output power and input power. But the condition is both of these two has to be measured in the same units. Means output power, if it is represented in kilowatts, the input power should also be represented in kilowatts only. So now coming to the efficiency of transformer, the equation is given by output power by input power, where input power is equal to output power plus losses, and the losses comprise of core losses and copper losses. The output power is represented as V2 I2 cos phi in this particular equation. So the efficiency of a transformer can also be represented in this form, where X is the fraction of load on which the transformer is operating, kVA is the rating of the transformer, and cos phi is the power factor on which the transformer is operating. Efficiency can also be expressed as input power minus core losses minus copper losses divided by input power. In other words, 1 minus losses divided by input power. So now we have to derive the condition for maximum efficiency. That is the condition when the efficiency of the transformer will be maximum. So for this, we have to consider the equation for the copper loss, which is I1 square R01. I1 is the primary current and R01 is the effective resistance of the transformer as seen from the primary side. Iron losses is equal to hysteresis loss plus eddy current loss. The power input to the primary winding
of the transformer is V1 I1 cos phi. Now the efficiency equation for the transformer is given by input minus core loss minus copper loss divided by input. Now separating the fractions, we will get 1 minus copper loss divided by input minus core loss divided by input. Here in this equation, this square and I1 in the denominator and the numerator can be cancelled. So we will arrive to an equation in this form. Now differentiating this equation with respect to I1, we will get d neta divided by di1 is equal to the differentiation of 1 is 0 minus the differentiation of I1 is 1. So the equation will become R01 divided by V1 cos phi plus PC divided by V1 I1 square cos phi. The differentiation of 1 by I1 is 1 by I1 square. So now in order that the efficiency has to be maximum, the incremental change in the efficiency with respect to I1 should be 0. So now we have to equate this particular equation to 0, and rearranging it, we will get this equation. In this equation, V1 can get cancelled, cos phi will get cancelled, so that we will arrive to this equation. From this, we can conclude that the core losses will be equal to copper losses when the efficiency of the transformer is maximum. So this is the condition for maximum efficiency. So now if you want to calculate the primary current by using core losses and the resistance, effective resistance of the transformer, you can use this particular equation.
Now, to obtain the load corresponding to maximum efficiency, so we already know that the efficiency of a transformer will be maximum when the iron loss becomes equal to the copper loss. If X is the fraction of the full load kVA under maximum efficiency condition, so we already know that the full load copper loss is proportional to the square of full load kVA. So taking this equation into consideration, we can write like the copper loss under maximum efficiency condition is proportional to the fraction of full load kVA for which maximum efficiency occurs. So now dividing this equation by the first equation, we will get an equation like X by full load kVA whole square is equal to the copper loss for maximum efficiency divided by full load copper loss. So from this condition, we know that the copper loss for maximum efficiency is equal to core loss that divided by copper loss. And simplifying this equation for X, we will get this particular equation where X is equal to full load kVA into square root of core loss divided by copper loss. Now let us solve some numerical problems. The first problem states that the required no load ratio in a single phase 50 Hz core type transformer is 6000 bar 250 volts. Find the number of turns per limb on the high and low voltage sides if the flux is to be about 0.06 Webers. So here we have to assume that the transformer has no losses. That's why the primary induced voltage E1 is equal to V1, that is 6000 volts, and the secondary induced voltage E2 is equal to V2, that is 250 voltage. The maximum flux in the core is given here, 0.06 Webers. The supply frequency is 50 Hertz. So now we have to use the relation for the EMF induced in a transformer in the primary of the transformer. E1 is equal to 4.44 F phi m N1. So by simplifying this equation for N1, we will get this equation, which goes like N1 is equal to E1 divided by 4.44 F phi m. So now substituting E1, F and phi m here, you will get the primary number of turns. Similarly, you have to use the relation for the EMF induced in the secondary winding, that is E2 is equal to 4.44 F phi m N2. And simplifying this for N2, you will get an equation like this. So now substitute the value for E2, F and phi m here, so that you will get the number of turns in the secondary winding, that is 19.
In the second problem, a 125 kVA single phase transformer has a primary voltage of 2000 volts at 60 hertz. The number of turns in primary are 182 and the number of turns in the secondary are 40. Neglecting the losses, we have to calculate the no load secondary EMF, full load primary and secondary currents, and flux in the core. So to calculate the no load secondary EMF, we have to consider the equation for transformation ratio. Here, K is equal to N2 by N1. N2 is given in the problem, it is 40. N1 is also given, it is 182. So with that, the transformation ratio obtained is 0.22. So to calculate the no load secondary EMF, again we have to consider the equation for transformation ratio. K is equal to E2 by E1. So simplifying it and solving for E2, we will get E2 is equal to E1 into K. So E1 is 2000 and K is 0.22. With that, the no load secondary EMF obtained is 439.6 volts. To calculate the full load primary current, the full load kVA rating of the transformer is given. So dividing this by the primary voltage, we can obtain the full load primary current. Here 125 kVA, 125,000 divided by 2000 will give you the full load primary current, which is 62.5 amperes. So to calculate the full load secondary current, we can consider the equation for transformation ratio, where K is equal to I1 by I2. Therefore, I2 is equal to I1 by K. I1 we have calculated, it is 62.5 and K is 0.22. With that, the full load secondary current obtained is 284.37 amperes. So to calculate the flux in the core, so we have to consider any one of the two EMF equations. So I am considering the EMF equation for the primary winding. Here E1 is given in the problem, it is 2000. F is also given, it is 60. N1 is also given, it is 182. So now simplifying and solving for phi m will obtain the value for the flux in the core, which is 41.2 milliwebers.
For the third problem, a 25 kVA single phase transformer has 500 turns on the primary winding and 40 turns on the secondary winding. The primary is connected to 3000 volts at 50 hertz supply. We have to calculate the secondary EMF, primary and secondary currents on full load, and the maximum flux in the core. So to calculate the secondary EMF, we have to consider the equation for the transformation ratio, that is E2 by E1 is equal to N2 by N1. So here, except E2, all the three other parameters are known. So substituting N2 as 40, E1 as 3000 and N1 as 500, by simplifying, we can obtain the value for the secondary EMF, which is equal to 240 volts. If the power factor is not given in the problem, so we can assume it as 1. And on full load, the primary current can be calculated by dividing the full load kVA of the transformer by the primary voltage. So 25,000 divided by 3000 is equal to 8.33 amps. The primary current will be equal to 8.33 amps. Similarly, we can calculate the secondary current by dividing the full load kVA by the secondary EMF. So I2 is equal to 25,000 divided by 240 is equal to 104.16 amperes. So to calculate the maximum flux in the core, similar to that of the previous problem, we have to consider the EMF equation. So E1 is equal to 4.44 F phi m N1. So E1 is known, which is 3000. F is 50 hertz. and N1 is 500. So by simplifying it for 5m, we'll get the value 0.027 Webers. In the fourth problem, in a 25 kVA 2000 bar 200 volts single phase transformer, the iron losses are 350 watts and the full load copper losses are 400 watts. We have to calculate the efficiency at 0.8 power factor on full load and half full load conditions. First, let us consider the condition of full load. So here, the output equation is given by x kVA cos 5 kilowatts. So under full load conditions, x is equal to 1, the kVA rating of the transformer is equal to 25, and the power factor given in the problem is 0.8. Therefore, the output at full load condition is equal to 20 kilowatts. Next, the iron losses given in the problem is 350 watts, which is constant irrespective of the variation of the load. The full load copper losses given in the problem is 400 watts. Therefore, the total losses is equal to 350 plus 400 is given by 750 watts. If it has to be represented in kilowatts, it is 0.75 kilowatts. The total input to the transformer is equal to the output, which is 25 kilowatts, and the total losses, which is equal to 0.75 kilowatts. Therefore, the total input is 20.75 kilowatts. Therefore, the efficiency at full load is given by output by input. Output is 20 kilowatts, input is 20.75 kilowatts. This gives us an efficiency of 90.38%. Next is the half full load condition. So in this condition, first the output at half full load has to be calculated. For that, the same output equation x kVA cos 5 kilowatts has to be considered. So here x is equal to 1 by 2 because it is half load. So 25 is the full load kVA rating of the transformer. The power factor given in the problem is 0.8. So the output at half full load is given by 10 kilowatts. Next, we have to calculate the copper losses at half full load. We know that the copper losses are proportional to the square of kVA. Here, as you can see, the kVA is being multiplied with 1 by 2 because it is half full load. Therefore, we have to multiply the full load copper losses by the square of 1 by 2, which will give the copper losses at half full load, which is 100 watts, as you can see here. Therefore, the total losses will be equal to iron loss, which is constant, 350 watts, and copper losses at half load, which is 100. So the total losses will be 450 watts. With respect to kilowatts, it is 0.45 kilowatts. The total input to the transformer at half full load condition is equal to output, which is 10 kilowatts, and losses, which are 0.45 kilowatts. So total input is 10.45 kilowatts. Finally, the efficiency at half load is given by output by input, which is equal to 10 kilowatts divided by 10.45 kilowatts. This gives us an efficiency of 95.7%. In the fifth problem, a 40 kVA transformer has iron loss of 450 watts and a full load copper loss of 850 watts. If the power factor of the load is 0.8 lagging, then we have to calculate the kVA load at which maximum efficiency occurs and the maximum efficiency. So to calculate the kVA load at which the maximum efficiency occurs, we have to use this particular formula where x is equal to full load kVA into square root of the core losses and full load copper losses. So the kVA rating of the transformer is 40. The iron losses are 450 watts and full load copper losses are 850 watts. So this gives us the kVA load at which the maximum efficiency occurs, which is 29.1 kVA. So to calculate the percentage maximum efficiency, first we have to calculate the output in kilowatt. So we have to multiply this value with the power factor of the load, which is 0.8. This gives us the output in kilowatt, which is 23.3 kilowatts. So we already know the condition for maximum efficiency. For that, the iron losses must be equal to the copper losses. So here, iron losses are given, which is 450 watts. At maximum efficiency, the copper losses should be equal to iron losses. So it should be equal to 450 watts at maximum efficiency. Therefore, the total losses at maximum efficiency will be equal to 450 plus 450, that is equal to 900 watts. So in kilowatts, it is 0.9 kilowatts. At maximum efficiency, the total input to the transformer will be equal to the output of the transformer, which is 23.3 kilowatts plus losses 0.9 kilowatts. Total input is 24.2 kilowatts. The maximum efficiency is given by the output, which is 23.3 kilowatts divided by the input, which is 24.2 kilowatts. This gives us an efficiency of 96.28%, which is the maximum efficiency of the transformer. So that will be all with respect to transformers. Thank you.